So this is homework 6, question 2, the design question. And this design question says you want to build an amplifier that gets maximum power transfer from a 50 ohm antenna. What that means is that you have an antenna and that's coming in, and you need an amplifier here to amplify that signal coming off the antenna. But the requirement is that this is seen as 50 ohms looking this direction. This is 50 ohms, and by the maximum power transfer theorem, that means that looking this way you also have to see 50 ohms. If you match the impedances, then you get maximum power transfer. So that's part of the spec. Okay, gave you the value for VT, and the supply voltage is 6 volts, and this is a design problem, not a simulation problem. So using calculations, small signal analysis, and the lot. Okay, so first one is asking what kind of amplifier this needs to be. Now all of your amplifiers, if you have a common source, Rn is infinite, so you're not going to get 50 ohms that way. For like a common emitter, your Rn is R pi, which is your beta VT over IC. This VT over IC for the, let's say for 1 milliamp, I don't think I specified that, right? For 1 milliamp, this would be, 5K or something. So if this was 25, and this was even just, if this was, and beta was 200, then you'd have 5K. So this won't work either. The Rn is too big. For a common drain, you don't get a common drain or a common collector, you don't get any gain, so it's not, you can't really amplify the signal. So those are out. What's left is a common base or a common gate. And I already told you that you want to use BJTs just because the model I gave you was MPS 650 and MPS 750. So these are BJT models, and so you're not going to use a MOSFET. So what's left for 1A is it has to be a common base. Okay. So first thing you want to do is find an equation, since the only specification that was really given to you. So the only specification given to you so far is that the RNs match. So the next thing you have to do is find an equation for Rn for your amplifier. So you've figured out that you want to use a common base. So now you need to do small signal analysis. To find Rn. And you're looking into the emitter. I put the details of small signal analysis on the solutions, so you can look at those. But what you get is, after going through all the work, you get something that looks like 1 over GM. And if you look at our quick method, anytime you're looking into the emitter or the source, that's what you see, 1 over GM. Okay. So now we have an equation for Rn, and the specs gave us a value for Rn. So actually there's question 1C before that. The first thing you always want to pick is current. So you may have an equation with two unknowns. One is the current and one is, say, a resistor value. You could just pick a resistor value and find the current that works with that resistor, but having a too small or too large resistor won't ruin your circuit, but having too much current or too little current, that could make your circuit not work. So you always want to look at the transistor. They generally have lots of tables or lots of graphs where they show the range that they think the transistor works well, whatever it might be. And you want to operate your transistor in a range that will make that transistor happy. So for the 650, I think it's 1 milliamp to, like, I don't know, 500 or something. I can't remember now. But yeah, usually you want to pick the current first, just because it does the most damage if you pick it wrong, and it can use power if you pick something too high. And a lot of devices made these days are for wireless devices that have to run on a battery, and you just don't want to run down the battery. Okay, so question 1D is to find that current, and the only information you have so far is that Rn of the common base equals 1 over Gm, and you also know that your boss gave you a spec, so that has to equal 50 ohms. And you know Gm equals Vt over Ic. That's wrong. Ic over Vt. And the reason I knew that is I just did a quick check on units, and V over I is resistance, and this is transconductance, so I knew I had it upside down. So 1 over Gm is this flipped, so Vt over Ic equals 50 ohms, and then if you flip that around, you get Ic equals Vt over 50, and you know Vt is 25.9 millivolts, and this is 50 ohms. And if you work that out, what I got here is 0.518 milliamps, sorry. Okay, so now we have our current. So the next part of the question was, you're making a common base. So if you draw a common base, it looks like that. You know the current, and you want the other part of the question is to make it a general purpose amplifier. And if you look at the VTC, what happens is it's high, it comes down, and then it kind of flattens out. This is where your transistor is going into linear. Down at the bottom where the graph kind of flattens out, I didn't draw that very well, but where it starts to flatten out, it's gone into linear, and all of a sudden your gain is reduced by a lot. So what you want to do is you want to take it in the active region, forward active if it's a BJT, saturation if it's a MOSFET, and the way to figure out where your transistor's in the active region is you figure out what the lowest V out can be. And that means V out, if V in is, your average is 0 volts. So V out min, the lowest this can go is 0 volts if that's what this is, if your input is a sine wave, if this is 0 volts. If your V in is a sine wave around 0 volts, then V out needs to be at least a VCE sat above V in, or your transistor will be in linear, and you want your transistor to be in the active region. So the lowest this can go is actually VCE sat, and the maximum V out can go is forever. As the rule says, if VCE is greater than VCE sat, then we consider this transistor in the active region. So anything over VCE sat is good, but we have this supply up here, so this can't go above the supply. So even though in theory any voltage on V out above VCE sat puts your transistor into the forward active region, we know that V out can't go above the supply voltage if there's no capacitances and inductances in the circuit. So now we have the max and min. To make it general purpose, you make the default value as the input to your amplifier. You make it so it puts it right in the middle between your V out max and your V out min. Put it right in the middle, and the way to do that is just to add the two. Divide by 2. So the average of these two is going to be right in the middle. So now you have what V out sits at rest, and you have the current from the previous problem. Your IC at rest is 0.518 milliamps, and you know that your V out, what did I get that to be? IE was, okay, I got V out mid was 3.14 volts. V out mid. And so what I need to do is I need to drop, the supply voltage is 6 volts, and this is the voltage at the output. So I need to drop this much voltage across the resistor, and I know the current. So that's the voltage I'm dropping, and the current is 0.518 milliamps, and that should give us the RC. Okay, we know it needs to drop this voltage when there's this much current, so that will give us our value of RC. And what did I get for that? 107? Oh, sorry, 5521.2 ohms. Okay, then IF, question for F. Whoops, I got this all wrong. So E was V mid. E was V mid. RC was 1G was RC. Whoops, no, 1F was RC. 1G is to find the gain. And we know for a common emitter, we know the gain equals negative GM RO parallel R. And your RO is probably really big, but let's go through it anyways. GM is IC over VT. RO is your VA over IC, parallel with R, which is 5.5K, I think, something like that. Okay, 5.5K approximately. This right here, if you look at the model file, that's for 750. For the 650, Not sure I have it up. Model 650, your early voltage is 100 volts. So when you figure this out, that's 100 over 0.0005. So this is, first of all, it gets multiplied by 1,000, or 10, 100,000. So this is 100,000, and then it's actually twice as much as that. So this is actually 200K right here, in parallel with 5K. So this right here equals approximately IC over VT negative, times 5.5K. And if you work it out with the extra decimal points here and with RO, it doesn't change all that much from this. And I got negative 107, I think. Nope, wrong homework. I got negative 107, I think. Okay, things are freezing. There we go. It's got negative 107. This should be negative. All right, since I'm here, let me fix this real quick. I'm going to pause the video. Okay, so there's that. And then the next is we're adding a common collector. So we have our common emitter, or common base, sorry. So is this H? Not sure. 1H. So we have our common base. And this has a regular, comparatively high R out. It's R in parallel with RO. So if you connected it to something and something pulled current, it would change your voltage here. So let's do call this RE, this RC. And let's see, what was the question again? So okay, again, at a common collector, what's the loading factor? Okay, so for the loading factor, what you need is the Rn of the common collector, and that's shown here, the R pi plus Re times 1 plus beta. And you can figure out the values by replacing your R pi with your beta VT over IC and getting the beta from the model file. And if you work that out, people got a little bit different answer than me, so I did go back and check the math. I got 459K for the Rn, and what is the loading factor? Okay, and we have the R out, which is RO in parallel with RE, and RO is so big that it's RC. RO in parallel with RC, and RO is so large that it kind of works out to being about RC, which was 5.5K. So let's see. So you have your, well, it's not 5.5K, but your 5 point something K. That's in parallel with RO. I think I went through the math, and that drops your resistance. Even if it's a really big resistor in parallel with a smaller resistor, the smaller resistor is dropped a little bit. So this is in parallel with RO. This is your Rn from the common collector. And the divider goes the Rn of the second circuit. So if you have two circuits cascaded, so the output of one is connected to the input of another, it's the input of that second circuit over the input of the second circuit plus the output of the first circuit. And if you work it out, you get about 98.8% of your signal going through to the common collector. Okay. For I, last week we assumed that the gain of the common collector was 1, and we didn't need to do any math. But this time I wanted you to I wanted you to do a little more small signal analysis work. So I asked you to find the gain of a common collector. And that work is here, so I won't go through it. But you find big GM and you find R out, and you multiply the two to get the gain, and it comes out to this nasty equation right here. And if you plug in everything, what you end up with is a gain of 0.988. So really close to 1, but not quite 1. It's just a little bit less. And the touchy-feely question on the next homework, the homework after that, this week's homework, homework 7, asks you to do the touchy-feely analysis of why the common collector has a gain of a little bit less than 1. This small signal analysis shows that it does. Okay, so now you have the gain of the first stage, the loading factor, and the gain of the output stage. To find the gain from the input of your common emitter to the output of the common collector, including loading, you multiply the gain of your common base times the loading factor times the gain of the common collector. And you had 107 before, and now you have 104. So it dropped it a little bit. And that's, if you want more detail on any of these steps, please write.